Hi everybody, today I'm going to talk about the power stage of my electronic speed controller. I'm not completely sure on the specs of the motor I have, although I do know it is a 12 volt motor and it can easily draw up to 10 amps. There are a few points I'd like to make first of all. This is my first speed controller. Electronics are not my area of expertise and just the general lack of specifications on the motor. I found that I could go in circles just over analysing all the components and comparing details. This results in just not getting getting anywhere with the project, and just too much procrastination. I decided to pick up a MOSFET that had a good balance of features and then build from there. I chose an IPP060N06N from Infineon, and as you can see, it has a drain source voltage of 60 volts. It's a reasonably low resistance for RDS on of 6 milliohms. It can handle 45 amps and a reasonable gate charge. So this should help with turn on times. So the overall layout, it's a very standard gate drive for a brushless DC motor. I did add 10k resistors here between the gate and the source to help with ensuring that the MOSFETs were turned off. Also added a flyback diode here to assist with dealing any inductive spikes across the MOSFETs. I chose an STPS1150 from ST. I chose it because I could get it as through hole. The 150 volts that spec 4 provides plenty of headroom, and being a Schottky diode helps with fast conduction times. It is only good for 1 amp, which may prove limiting if I start to look at regenerative braking. So regarding then the gate drives, first of all I should state the gate drive that you see at the moment does not have any current sense. I just omitted them just to make ease of manufacturing for it. The new printed circuit board will have current sense resistors on them. So the gate drivers themselves, there are a few different techniques for switching high side and channel MOSFETs. I decided on using the UCC 27710 half bridge gate driver from Texas Instruments, which uses the bootstrap technique. So some reasons why I chose it are it handles the voltages that I'm looking to use. It accepts a 3.3 volt at the logic input. It has output interlocks to ensure I don't get any shoot through. It can independently control each output as long as there is sufficient charge in the device, and it provides a great application note on how to size the components supporting it. So we'll go through that, and here's just a general layout of it. So your microcontroller input here, and then here's your outputs going to your gates via MOSFETs. So the application note, you scroll down here, it's really well written out. So their application note is running off a 650 volt MOSFETs and 100 kilohertz switching frequency and a DC link voltage of 400 volts. So yeah, we're not going to worry about that, but their schematic here is exactly how I've wired it up here in KiCad, and so let's just go through some of the components. Here they've got high and low pass filters for the microcontroller. I chose to omit that just to save time and complexity. I'm debating whether to implement them on the PCB version. Now regarding the bootstrap capacitor, I just followed the formula here. So the bootstrap capacitor is this device here between pins 8 and 6. So you can get your gate charge from your data sheet. So 27 nanocoulombs for the gate charge can just be found here. Gate charge total, so that's where I got the 27 nanocoulombs from. IQBS of the gate driver is 65 microamps, so it's just taken from this data sheet. And yeah, and then I chose a switching frequency of 50 kilohertz. So plugging that into the formula provides a 28.3 nanocoulombs for Q total. To provide a ripple voltage of 0.5 volts, we divide our Q total by 0.5 to give us 56.6 nanofarads for the bootstrap capacitor. Following the application note, they make some good reasons why to increase the bootstrap capacitor. So I also chose to use a 220 nanofarad capacitor. Now to select the VDD capacitor, the application note recommends it be 10 times larger than C-boot. So 2.2 microfarad capacitor was used. Also, I selected a 10 ohm resistor for R bias as per its recommendations. As you can see, I'm really just following the application note. This should provide myself with a device that I can get up and running and start to conduct testing on. From there, I can refine it if and when I need to. So just continuing on, R boot here, that's this resistor here, is used to just limit the current in the diode. There can be large currents during initial charging of the bootstrap capacitor. I selected a 2.2 ohm resistor value. Also, as I'm working with the similar components and voltages, the bootstrap diode selected was the BYG20J, as it was recommended. Not sure why I chose it over the other device, possibly a cost reason. And then now to calculate the gate drive resistors, as like before, I just follow the data sheet. I have a caveat here though, as I've not checked though if the 0.5 gate drive current for this device is suitable for the FETs. I've not checked their input and output waveforms. This is something that I want to understand better for the next revision. Ideally, if this gate driver is undersized, I can find a replacement one with a higher source and sink current rating. Now, like before, just following the formulas, and I land on the following resistor values. So I need to make sure the current is at 0.5 or lower. So I rearrange the formula here for R on in my particular case, and the high side and low side source resistors. So the high side is 14.8 ohms, I calculate, and the low side is 16 ohms. So as you can then see here, I increase my 14.8 to 15, and I leave the low side as 16 ohms. And then the high and low side sinking currents, they have an additional voltage drop across the diode for the sinking, and we have a limit here of 1 amp now based off the data sheet. So just rearranging for R off, my high side R off resistor is 6.85 ohms, and that is I use a 6.8 here, get pretty close, and then the low side R off is a 7.45 ohm, which is rounded to 8.2. And so yeah, as you can see, just follow the data sheet, and then from there, it's provided me with based off the video in the last video, it's worked pretty well. Next video, I'll possibly talk about the I'll talk about the position sensor feedback and the throttle pedal input. Pretty simple, but yeah, I can talk about that, and then I can talk about the code later. Thank you very much. Bye.